In Chapter 13, we were only dealing with trig functions for right triangles. But in Chapter 14, we want to start looking at how we find these trig functions for any type of angle, even if it doesn't come from a right triangle. So if you've not taken a pre-calculus class, you're probably not familiar with anything from this section. So hopefully you can look at how all of these pieces work together and how they do apply back to what we did in Chapter 13, but it's going to take on a whole new perspective with how we deal with trigonometry. So the first thing that changes is instead of dealing with an angle in a triangle, we're actually going to deal with an angle in the coordinate plane. So here in the coordinate plane, we have our x-axis and our y-axis. And the way that we measure angles in standard position is we start with one ray on the positive x-axis there, and we call that the initial side. Then the angle is measured as the rotation of that initial side until you get to the terminal side. And so the terminal side will be the side that's not the initial side, and the angle is going to be defined typically as the counterclockwise rotation that you had to create to form that angle. So let's call this the terminal side, and that would be in standard position. Now your positive angles will go in this positive direction where it's counterclockwise, but you can also have a negative angle. So maybe we have our terminal side here, and if we want to form an angle here and we want to measure it from the x-axis down to that terminal side, that would be a negative direction. Now, sometimes you'll have an angle that will end up on one of the axes, and those would be quadrantal angles. So this would be an angle like a 90-degree angle, or a 180-degree angle, or a 270-degree angle like that. So now that we're dealing with basically a whole circle's worth of values, we're going to be able to have angles from 0 to 360. And so that's very different from what we dealt with in the previous chapter. But let's finish some of these definitions and then we'll look at these quadrants. So your quadrantal angle is where it coincides with one of these axes. So a 0-degree angle would be the angle that starts and stops right there on the x-axis. And then if it ends up at the positive y-axis there, that would be a 90-degree angle. If the angle makes it all the way over to the negative x-axis, that would be your 180-degree angle, which is basically a straight angle that we've had before. But here's the thing, we can keep going. And so if we made it all the way to this negative y-axis, if we had gone like that, that would be a 270-degree angle. And if you make it all the way around, you could have a 0-degree angle, or you could actually define that as a 360-degree angle if it's gone all the way around. So any angle between 0 and 90 is going to be in what we call the first quadrant. Any angle between 90 degrees and 180 degrees is going to be in what we call the second quadrant. Anything between 180 and 270 is in the third quadrant. And anything between 270 and 360 is in the fourth quadrant. And we use Roman numerals here since we have so many other numbers floating around. It just makes things a little bit easier. And then with that positive and negative angles, we'll note here that a positive angle is formed when you go in a counterclockwise position. So it might seem a little weird at first, but when you're opening up your angles, you are traveling in that counterclockwise direction. Negative angles are formed when you rotate in a clockwise direction. So let's look, or actually these little pictures are here for us to look at positive angles. So maybe I wanted to have about a 225-degree angle that would end in that third quadrant, and I would get there by measuring positive 225. But I can actually have an angle that looks exactly the same. I guess technically I'm on the positive x-axis as well. But I can get the same exact angle here, but going in the negative direction. When I go in the negative direction, I end up going negative 135 degrees. So it's kind of strange that you can get these angles that end at the same place, and we call these coterminal when they end up in the same location. And you get coterminal angles by simply adding or subtracting 360 degrees. So you can see here, if you subtract 360 degrees from 225, you end up with negative 135. And that's where you can see that these are the same looking angles, even though they have a different value. So now that we have angles that aren't in triangles, how are we going to be able to define the trig functions for them? We still will have sine, cosine, tangent, cosecant, secant, and cotangent, but now our angles can be any value. Well, let's connect it back to a right triangle. So I want you to imagine you have this angle, this terminal side, and since we're in a coordinate plane, it's going to have some x and some y coordinate. Now remember, the x is the distance traveled on the x-axis, and the y is the distance traveled in the y-axis. Now, x and y can actually be positive or negative depending on where you are in the coordinate plane, so we do need to be prepared for that. But I want you to think about how we dealt with these as right triangles. Well, remember, sine was opposite over hypotenuse? Well, it's actually still the same thing, because if our angle is here, theta, the opposite side is essentially the y value in the coordinate plane. And r is basically the hypotenuse. R is going to be the length from the origin to that coordinate. So we'll define sine as y over r, but it really is still the opposite over the hypotenuse. We just don't have the same type of right triangle that we had in chapter 13. Now, cosine would be adjacent over hypotenuse, and that x direction would be that adjacent side. And then tangent, opposite over adjacent, you see y over x, and then the reciprocal functions, you see that we're just flipping over. So now we can actually define any angle, and it's going to depend on the size of the angle. And it won't matter what, how long that radius is, because it will still be in the same ratio between y and r, or x and r, or x and y. So we're just looking at this from a slightly different perspective. So let's see how this would look in an example problem. So instead of us having a right triangle, instead we have an angle that we know goes through the point 3, 4. So remember, with ordered pairs, you travel on the x-axis first and then on the y-axis. So I go 3 units to the right for positive 3, and then 4 units up for positive 4. So that point 3, 4 is there in the first quadrant. Now my r is going to be the distance from the origin there where it crosses to that point 3, 4. So we can think of this as a right triangle with 3 on this side and 4 on that side, and we can still do Pythagorean theorem. It turns out our r is going to be equal to x squared plus y squared, and you take the square root. And that's just Pythagorean theorem. A squared plus b squared equals c squared. You take the square root. That's all we're doing. So here we have 3 squared plus 4 squared under the square root. That's the square root of 25. So our r here is 5. And now we can find sine of this angle is going to be 4 over 5. Cosine of this angle is going to be the x value, 3 over 5. And tangent of this angle is going to be 4 over 3. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So we're connecting to what we had in chapter 13, but this is just a different perspective. Now let's look at example 5. Here we have a point on the terminal side at negative 1.5, 3.5. So now we need to actually go in the negative direction for x. So my negative 1.5 is going to be in that second quadrant, and I go up 3.5. So I've got a point at about that location. So here I got into the second quadrant because my x value was negative. This direction is the negative x direction. Well, I need to get my r. In order to do that, my r is going to be the square root of x squared plus y squared. And in this case, my x is negative 1.5 squared plus 3.5 squared. Now be super careful here. You absolutely have to do that negative 1.5 in parentheses. If you don't, the calculator will not treat that as a negative number that is squared. It will square the number and then put a negative in front, and that is not going to be the right answer. So in some ways, you're almost better not putting in negatives at all when you do this on the calculator. But you have to put a negative value in parentheses before you square it. So on this one, you should get about 3.81 as your value for r. And so you can think of this negative 1.5 in the x direction, 3.5 in the y direction, and then 3.81 in the r, the radius direction. So to do this, we just do those same ratios, sine of this angle, and even though this angle is found by rotating, so it's actually starting at that starting position and rotating into the second quadrant, we're still going to treat it as that right triangle there going down to that negative x-axis. And we'll talk about this. It's called a reference angle, and we'll talk about this later on this section. But for right now, sine is y over r, so 3.50 over 3.81, and you can just leave it as a fraction. Cosine of theta is going to be negative 1.5 over 3.81, and tangent will be 3.5 over negative 1.5. Cosecant is the reciprocal of sine, 3.81 over 3.50. Secant is our reciprocal of cosine, 3.81 divided by negative 1.5, and cotangent of theta is negative 1.5 over 3.5. Now, a quick note on where you write the negatives. Typically, writing a negative in a denominator is really not an appropriate place to do it. So for this tangent value, I really should have that negative just either in front of the whole fraction or up in the numerator. It's really not appropriate for it to be in the denominator, but it's certainly okay to divide by a negative number. It's just a weird way to write it. Same with secant. I should really put that negative in front. So it's not wrong if you have a negative in the denominator, it's just not what is typically written.